N sides. What do we call an 8-gon? What do we call a 2-gon?
Yeah,
A
right.
straight line. They don't exist. They ain't polygons. Good. A 3-gon. How many diagonals does a triangle have? Oh, this is cool. So wait a second. Wait a second. You mean to tell me that if I worry about this issue of number of sides and number of diagonals, that you're able to sit there and say 3 sides, no diagonals? Because a triangle just doesn't have any. What's that called? A square or a quadrilateral? More than 2, I like that answer. How do you know? Because it's bigger. Oh, cool. Why 5? Because I counted them. 1, 2, 3, 4, 5. Oh, it's that star. It's the pentagram. Oh, cool. And I want to draw out the stupid pentagon. I want kids to sit there and go, I don't know. 1, 2. I can't do any more from there, can I? Oh, 3, 4. Oh, 5. Yeah, the devil's going to get you, right? I mean, it's all. So I got 5 of these things, but you also start to see that from this vertex, I can draw 2. Is that right? From this vertex, I can draw 2. From this vertex, I can draw 2. From this vertex, I can draw 2. So if there are 5 vertices and I can draw 2 from each vertex, there are 10 diagonals, right? Oh, but that means I count this one as this one and this one as this one, so I divide by 2. Oh, cool. So now, 6, I got a hexagon. Now some of you are seeing +2, +3, +4. Others of you are sitting there saying, wait a second, 6 times 4 divided by 2. 6 vertices, 4 places to draw it. Right over here was 3, no, 2, wait. Oh, 6 times 3, thank you. 6 times 3, that helps, right? Because you can't draw it to itself, or its 2 neighbors. Divided by 2. 10. Shouldn't we have a class where, in fact, kids are sitting there saying, +5, +6, +7, +8? And the other kid's sitting there going, yo, dude. What's the answer? Oh, so it's great. So I'm racing through this so quickly you don't even have a clue what's going on. You know why? Because I never did this thing that says, right, that it's 4 times 1 divided by 2. It's 5 times 3, 2 divided by 2. It's 6 times 3 divided by 2. It is 10 times 7 divided by 2, 35. How nice. I rest my case, gang. If you don't see that middle column, that I should have put this column in to help kids see what was going on, and I blew it by not having it in there. That's the thing that shows us this rule. And then lo and behold, God said, n times n minus 3 all over 2. God said, n squared minus 3n over 2. How are those the same? Well, let's see. If n is 2, what's this? If n is 2, what's this? I'll be damned. N is 3. N is 3. It's the same. So how do I move into quadratics? I go, good morning, guys and girls. Let's worry about this stuff. All right, wonderful. So there's the table. Do me a favor. Graph it. What happens when I graph that? Do I get a straight line? I can't hear you. Do I get a straight line? No. How do you know I don't get a straight line? Because I add the same thing every time. It's not like the cups, right? I'm adding 2, then I'm adding 3, then I'm adding 4. What does it look like when I add 2 and then 3 and then 4 and then 5? I have increasing slope. Oh my God, I have a rate of change that changes. I don't have a slope. Boys and girls, in mathematics, one of the most important ideas of all is that on a curve there is instantaneous slope. There is slope at a point, and that slope changes. But we're not going to do calculus because that would really blow your minds, but we're going to come back and do limits, don't worry. A table, a graph, an equation. I'm doing quadratics. I think that you see how that opens the floodgates to 2 of those problems we already looked at, right? We looked at the table. 1, 1, 2, 4, 3, 9. That's this stuff. we looked at this issue of which graph looks like it, and so I see the way these graphs work in that way. All right, now let's go back to rectangles. Take a deep breath. Perfect. God has given us a rectangle with a perimeter of 24. What more could you want? I'd like you to open your handout to this page, and I'd like you to write 5 and 6 in the left-hand column and complete the table. So far, so good? Look at how powerful this is. Look at the stupidity of a rectangle with a given perimeter, right? And so I know that I have this really cool relationship. Look at this. The length is 1, the width is 11, right? So I've got this point up here, right? The 10, 2, oh, I got this one. 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 I'll be damned. Look at this. Ladies and gentlemen, N. Beautiful thing is the perimeter, the semi-perimeter is 12, right? The length plus the width has got to add to 12 in every case. So if one of them is N or L, let's make this L so it's clear, then this is 12 minus L. How nice. That means that my area is L times 12 minus L. In other words, my area is 12L minus L squared. Uh-oh. Uh-oh, spaghetti-o. What does that look like? 111. Well, I love that. That's the same right there. 220. Uh-oh. That's up here. By the way, what happens here? That's right, it's 12, right? It's called a line, right? It just doubles back on each other, and the area is 0. So in fact, we do have this point right down there. Oh, not bad. How long did it take me before I got to this? That's pretty good. If I only dump this twice today, we will thank God. Right? So what's going to happen now? You know what's going to happen, right? In fact, and then I've got, it comes up, whoa, wait a second. But it goes by 9. Then it grows by 7. Then it grows by 5. Then it grows by 3. Has anyone ever seen this before? This is unbelievable. It's growing by a pattern, which means that the second differences are 2, 2, 2, 2. Have you ever seen a second difference of a constant 2? It must be quadratic. Well, what does it look like? It looks like, in fact, and as you know, it matches out at 6 because the next line in the table is 7, 5, 35. I don't know of a better way to take something as simple as, everyone has a piece of graph paper. We have, God said, perimeter is 24. You've got 24 inches or 24 things. Start drawing your rectangles. And so I've got this wonderful linear relationship of length versus height. And then I have this amazing situation where I get this perfect parabola that peaks at 636. We're right in the middle. And then you sit there and go, well, duh. At 0, 12, and at 12, 0, and we start building this idea of symmetry, which is going on, all because I take this idea that's not in enough of our books and make it work. Questions? Okay.
I want to share that I used to be a home builder, and I get calls all day long. How much does it cost to build?
People can't hear you. Yell it out, please.
Oh, I used to be a home builder. I used to get calls all day long. How much does it cost per square foot? Or how much for a 3,000 square foot house? I always said it depends on the shape and the length of the house because it's going to change the perimeter. That's, to me, I mean, that's a good real world application for the students.
Culinary school, we talked about this problem, okay? That everything is based upon flour when you do baking, right? So it's 2 parts sugar to 1 part flour, and then it's, so you've got, 8 ounces of flour, what do? And it's that same basic proportional relationship that goes on here, exactly right. So all because we sit there and do this. Erase, what do we do to erase it all? Where's the eraser? Oh, there it is.
No.
No, it isn't. Where's it?
Put the pen down and get the eraser.
Oh, bingo.
You have to put your.
Oh, this stupid thing? There's an easier way to do it. It's just erase. It's perfect. Right, so we've been there, we've done that, but it's going to come back up, isn't it? Did it stay erased or not? What am I doing?
Keep going.
That's the one we're working on, right? So, it's okay. Oh, but I don't care. It's not going to be here for the next one. It's cool. I'm going to stick on my PowerPoint. What do I care? All right, so, bingo, there it is. So there's the full thing. I graph it out. We see all those things. I go back and I go, boys and girls, what's a function? Does the function have to be linear? Am I making sense? And when I go back to these questions that I had, these are my guiding questions. This is what sits on my wall during this entire unit. And so when I forget, the kids go, wait a second, you forgot those key questions. I go, yeah, thank you, Jesse. Okay, so what's a function? A function is a relation between variables. Sometimes it's a line and sometimes it's a curve. This is really interesting. When it's a curve, sometimes it maxes and mins and ooh, right? Why are functions useful? So you can tell what's the biggest stupid rectangle you can make because you know it may be that you only have 24 feet of fence. And then you blow them out of the water by reminding them that if they want to enclose the greatest area with 24 feet of fence, you are not going to do a 6 by 6 square. You're going to do a circle that has a circumference of 24, but that's really calculus. Right? So we do this, we do that, and we get that. There it is. So what I just did is sitting there, okay? And so again, it's a matter of trying it out. Again, it's a matter of making the slides. It's stealing my slides. It's trying it out during some prep periods that you have. It's doing it at a team meeting and saying, well, let's see what this looks like. And then it's sharing those slides around. It's sending them to Emily and saying, hey, put these on the Math PLC repository so that we can use it because Steve's stuff was fine for teaching us, but it did not go far enough for teaching the kids and all those things. Length versus width, length versus area, let's look at the patterns in the table. What can we generalize about P? How do we know it? And I ask you, where's the math? And I think it's pretty clear. I'm doing this connection between linear. So we started with the skeleton tower only to whet your appetites about what we're going to do today, but now you see that it plays out in much more accessible ways. All right, take a deep breath. Good morning, my bright-eyed, bushy-tailed, troubled students. Most of you have sort of done okay on AIMS. We're still trying to make sure that everyone's coping with it. But you know, we still have a whole lot of math to do. The owners of a concession stand have determined what you all know. Right? Jessica, so now you see why I was so excited. I walk into Jessica's class this morning at South Point, and sitting on the board is the demand function for a camera is P equal 500 minus 0.5 e to the, sorry, good, I'm erasing it like a moron. Where's my eraser? Not that.
Put the pen down. No, in the cradle, yes.
Oh, you gotta be kidding.
It's not that smart.
Clearly, I'm not the one who's smart. This is so great. You know what? If it isn't clear to you that if I can do this, okay? You think that I use a smartphone on a regular basis, okay? No, okay? But if I can do this in front of you, you tell me you can't take some risks in front of kids. You know what? They'll help you. They'll figure it out and all that stuff. Sorry. So Jessica, e to the 0.000. No, just now I'm screwed. Put that down. I got too many zeros there. Now I got it. For what was the variable you had?
I think we used X.
X. How nice. You know what a demand function is? A demand function is that as the number that people buy or order goes up or down, the price changes. That's supply and demand. And in fact, most demand functions are not linear, right? They are, in fact, logarithmic. And so they are these really nice things. And so in Jessica's class, the question was, if P equal $300, what's the demand? If, in fact, the price goes up to 350, what happens? And so you know that I do the natural log, and I do all that kind of stuff out. And in fact, it comes out so that 300, they're actually going to get about 498 will be the demand. And at $350, it's only about 425 and all that stuff. Well, so I'm sitting there going, it was great. But that was it. Like, that was her warm-up. And it was amazing how 8 kids, pre-calculus, they're whipping through. By the way, you understand that the only reason that Jessica was able to do this is that there are other people in this room that did an amazing job of preparing these kids for that. And so I think we need to remember, this is not in 5 weeks because Jessica's a genius. This is because she's building on an amazing foundation. But look what I'm trying to do for you. I'm trying to help you see that whether you're teaching Algebra 1 with not a whole lot of quadratics, Algebra 2 with the quadratics we're talking about, or pre-calculus where you go beyond into log and log functions, then in fact, so I'm sitting there going, well, gee, what happens if the price is 1? I mean, not going to do 0, but, you know, suppose it's like $1 for a camera. What's so cool is when you plug 1 in for price, this has got to be $499, which means this is going to be $998. And so I press the buttons on my calculator and I got $1,728. Well, at that point, obviously, I want to graph it. I want to see how, as the price goes, look at that. The price drops off the face of the earth, but now the only thing that really is important and what Jessica didn't do is the revenue function. Because you're only going to set a price in order to maximize revenue. So you set the price at 1, you sell all these damn things, big deal. All you make is $1,728, right? Compare that to what would have happened way back here. At 300, you're selling 1,500 of them. My God, you're making $1.5 million at this particular point. That's revenue. Every one of you should be sitting there saying, let me have it. Let me draw it out. So where does that come from? How do you build that understanding? Well, you can teach an old dog new tricks, right? I'm able to sort of, what? Come on, get up. I don't have a pen. There's no way. Come on, get up there. Get up there.
That's weird.
All right, big enough. I hope you think this is. I'll think about you when I'm having dinner with my 3 brothers. An astronomical price tomorrow night in Wasika. All because of Leona Group. It's great. You ready? So the owners of a hot dog concession stand determined that when the hot dogs are priced at $1, whoa, at $1, they can sell 2,500 hot dogs. What do you think happens when they raise the price? They sell less. Why? Because no one wants to pay that much, right? Well, some people still do. Okay, so wait a second. So I sit there and go, whoa. What goes here? Okay, what good is all this stuff if every single one of your kids doesn't instantaneously understand that I don't care whether I'm in the world of Jessica's camera exponential log functions or I am back on the narrowest of carnival ride linear functions, what goes here? I can't hear you. What goes here? Not a number. Price. That's right. This is the price. Why do I put the price here and not the number of hot dogs there? I want to see, because that's the independent variable, because that's the one that moves and marches on. That what varies is the price. That's what I change in some particular way. And you knew that this was going to drive me crazy. There is a button that just allows you to erase it in one fell swoop. There has to be. What goes here? So, tell me about scale. Is it clear to you that the hardest thing in the world, if we don't have a graphic calculator, right, is the issue of scale, right? So, well, I mean, 0. I would think that I'm not going to be able to charge much more than $5 for these boogers, right? I don't think so, right? And then I got, so let's just put, I don't know, 2,500 in over here and see what happens. So far, so good?
Yep.
What do I do with the information that's in this problem? I plot it, I graph it, right? And I sit there and say, so let's see, at $1, 1, 2, 3, 4, 5, I'm up to 2,500. Oh, But at $1.25, whoa, let's see, so this is now going to be 2,000, 1,000, 1,500. I'm barely going here. Uh-oh, right, that's going to be, thank you. Now, everyone in your body wants to take out a line, right? So, I mean, the next thing that ought to happen is that I sit there and go, well, let's see. So, I've got 2 points. How much money do I make here? I make $2,500. How much money do I make here? Ooh, 750, 375, 1875. Huh. So, $1 plus 0 times 2,500 minus 0. That's where I start. But when I do 1 plus 0.25, now I start talking about 2,500 minus 1,000. Huh. Suppose that less 1,000 for each quarter change? So, for every increase in 25 cents, I have a decrease here of 1,000. My linear demand function, wait a second. My revenue function who thinks they know what I ought to do? Drop the price. But if I drop the price, I make less money. Oh, if I raise the price. Oh, so you think that I ought to do it this other way. Huh. So the linear demand function here is that I sell, right? This is the demand. Good. You put the eraser in there and it does red. That's really cool. So you put the demand, it is smarter than I knew, right? So this is the demand, this is the price. I'm confused.
Price always goes on the left.
Say it again.
I don't know about math, but in economics, price is always on the left, quantity is on the bottom, so you got me confused.
Ah, except that the price is what I can adjust. I can't adjust my demand, I can only adjust the price in this particular case.
I'm going to be confusing a lot of students.
Yeah, that's true. I know. That's, by the way, because of Samuelson. You know, he did that in those first set of books where, you know, everything was priced for a whole bunch of things because in so many ways price is responsive to other things. But why am I confused here? I'm confused because what I'm trying to do is establish that for every increase by 25 cents, I have a decrease in the demand by 1,000. And I ought to be able to find some way to write that mathematically.
Oh, wouldn't
Well,
it be
you-
like,
1 plus 0.25.
yeah.
You can at least make the connection because it's also
This is-
on the negative correlation and how when one increases and one decreases, you know, so you can throw that in there.
This is really wild. Let me show you what I thought I was trying to do and why I thought that it worked so nicely, but it didn't. This is really interesting. So here's what I'm trying to do, and I need you to help me right now. Gang, I have a price. Based upon the price, I have a demand or a number sold. So far, so good? And based upon the price and the demand, I have revenue. Okay? And so what I've said here is that I have a price of $1, I sell $2,500, and I make $2,500. That was given to me. I said to you that if I raise the price to $1.25, my demand drops to $1,500. And my revenue here becomes $1,875. So I have those 2 points. Now what I'm trying to do is say, wait a second, for a price P, what is my demand? And then what is my revenue? That's what I'm trying to do, and that's what I'm screwing up. So, when this goes up by, right? So this is
6 times 0.25.
1.25.
Because the demand is X, and then the constant is about.
So whatever my price is, right? My demand is 2,500 minus 1,000, but for each of these 25 senses. So why am I screwing up? What am I not seeing?
Minus 4,000. 4,000.
Minus
1,000 divided by a quarter.
This is so great. Do you realize what we're doing here? I mean, I don't understand whether or not I'm totally confusing you, or whether you think this is harder than it is, right? But in fact, all I have here is 2 points, right? And I'm saying that it's a linear demand function. If I have 2 points, then I ought to be able to sit there and simply say, well, look what's going on. I have a matter of the change in y is 1,000, and the change in p is 1/4. The change in y over the change in x, I have a slope of 4,000. So why am I so screwed up on this thing? Very simply, I'm going to tell you why in a second, right? So if I have p, this number here, this number, and this number is my slope, 4,000 p. Talk to me.
Negative 4,000.
Minus, or is that the minus part?
Negative 4,000.
Minus
So that's, the is negative.
Yeah, it's negative 4,000 P minus 1,500.
when p is 1, that works. When p is 1.25, this goes up, but this goes down. That's not going to work.
Plus 6,500.
So it's 4,000 p.
I think it's supposed to be a negative 4,000 P because your slope, and then when you find your y-intercept, it'd be plus 6,500.
Well, it's not 45, it's not, yeah.
Hold on. If p is 1, if p is 1.25, that's embarrassing. I want you to know that I spend most of my life saying, if you dare to walk into a class and do complex problems, not having done those problems out the night before, you are an unprofessional boob. And in case it isn't obvious, you just got an unintended modeling of unprofessional boobism. I'm so smart, I can do these things, I've done them before. I did this 6 months ago, and I'm so distracted with so many other things. I'm on target, I went through all these other slides that I haven't done recently. I knew I could do this one, and look what happened. It was terrible. Now you take a deep breath, right? And you sit there and go, what's missing from this is a notion of a demand function based upon 2 points. And now that I have this, The whole purpose of this is to now get the revenue function, which is the product of these things. Because the revenue function is now minus 4,000 p squared plus 6,500 p. And guess what, gang? It looks like this. And every one of you in this room wants to sit there and say, duh, what's this point right here? How do I get there? And now finally we have a reason to go and solve a quadratic formula. Help me. You are in the real world. You've got to solve this problem. How many of you are going to go to the quadratic formula? Yeah, that's right. The right answer is here. You got to be kidding. Right? How many are you going to complete the square? Well, then what are you going to do? You're going to take out your damn graphing calculator, right? And save me.
Oh, G-solve max.
So you what?
Do the G-solve function.
Yeah, you do the G-solve and the function right there on the calculator. Have you done this? Or you're busy doing other things?
No, we did this. Basically what I would do, though, is I would just differentiate the polynomial and solve for 0.
Ah, well, of course.
It becomes a linear and you solve for 0
Yes,
yet.
of course. Those of us that have calculus understand at this point we tell kids that all you have to do is sit there and write and save. That the beautiful thing about this is it's minus 8,000 p plus 6,500, right? Because there is a p in here, right? And this thing is equal to 0 when?
Yeah, let's see.
When p is equal to, so take out your calculators, right? And see that. It matches out when you are spending about 75 cents per hot dog. Actually, that's probably closer to about 78 cents per hot dog. How nice. And then the question is, you're never going to do 78 cents, so you round it to 70 and then charge tax or all those kinds of things. So far, so good? Wonderful. Now, if we had all day, okay, I would sit here and say, aha. So, I did this cool problem and I did a terrible job on it and all that kind of stuff, and now we're all totally confused. And so fortunately, I have what you need to always have going in, and that is the back pocket problem. You need to always sit there and go, well, what happens if it blows up? What happens if I screw it? Or, what happens if it works great, but I really don't know what anyone's learned? Well, guess what? I now have exactly the same amount. High school charges $250 for admission, and 2,000 people show up. When they raise it to $350 because they're being picky about it, the attendance falls to $1,500. They made more money. Is it clear? 5,000 bucks. Yes? Right? Whoa! 5,250 bucks. Yeah, made more money. And everyone says, why don't you charge $4? You can hear the athletic director. Why don't you charge $4? And then we math people come in and blow the whole thing out of the water. I think that now we see that if I'm in Algebra 2 and I'm trying to make sense one more time of a situation that gives me linear and quadratic, I'm able to say 2 points, a linear demand function. I'm able to convert those 2 points into the equation. I then multiply the price by the demand, and I have a quadratic that I have to graph out and go on and hopefully do it more effectively than the one I just did. Take it easy. So it's Friday. You're now in the 3rd quarter. And it's a Friday and you finished up early and all that stuff. And you're trying to review these things. We still have this damn Ames test sitting over our head. And so I walk in and I go, boys and girls, what do you see? Yell it out. You see a pattern, a table, numbers. How many numbers? What about these numbers? Tell me about these numbers. They're all even numbers. And they decrease by 4. Wonderful. So that's all I want you to see, that it decreases by a constant amount and wonderful and all those kinds of things. Great. Aha. Talk to me. They're still all even? Yes, they are. Down by?
86.
Ooh. Which means the second difference will be 2, 2, 2. If this is linear, these tend to be quadratic. How nice. Help me. Ooh. Oh! Clearly, I have left the world of constant adding and stuff. Talk to me. Difference of 12. Where did the 12 come from? That's 10%. What's the 10% of this? What's 10% of 108?
10.8.
And lo and behold, that's 10.8. What's 10% of this? And lo and behold, wonderful. Good. What do you call this? You call that linear? How do you know? Come on, gang. How do you know that's linear? Kid says it's a common difference. Kid says if you graph it out, it's a line, right? Kid says that, right, there's a constant difference as you go down. When this changes by 4, the other changes by whatever. One changes by 1, by 4, whatever that is. Wonderful. And this one? That one's quadratic. Wonderful. Whoa. What changed? Yeah, all of a sudden that left-hand column screws everything up, right? As always, the left-hand column is data. And so now you have all the information. Tell me the story about Tom, Ronnie, and Jamie. They are students. Good. They are on
Biggest Loser.
The Biggest Loser, which means that these 3 kids are, they're fat. Or all of them fat. If they're high school kids, well, you see, there it is. If it took me an hour and a half to finally get 2 people in this room to start laughing, I've succeeded. Thank you. It's there on bias. It's like, oh, is that what that thing is? And the kids are right there saying, cool. Ladies and gentlemen, what good is any of all this stuff that we've been doing? If you can't sit there and say, after 8 weeks on the damn diet, where are they going to be? Right? If you can't sit there and say 4, 4, 4, bingo, it's going to be down to 142. Yeah, it's 8, it's 6, it's 4, it's 2. The kids tell me that Tom is going to weigh 202 after 8 weeks on the diet. Look at Oprah. They really... 10%, Ronnie's going to die. I mean, Ronnie, no one should be losing a proportional amount. I mean, it's just ridiculous, right? I mean, this is, Jamie's going to disappear in 31 weeks. Right? So, in fact, this is an insane situation, but I need kids to understand that, in fact, healthy dieting is quadratic. Healthy dieting is actually exponential, right? Healthy dieting is losing some percentage, but a decreasing percentage, not the same My God, you lose 10% down here, right? Please! You know, the first 10% is easy. And so look what I've done. I just give you these stupid things, and then what is each fish worth after 8 weeks is what that should be. Who's doing best so far? Help me with this. Convince me that Tom is doing the best. Tom's doing best because it's realistic. Tom's doing best because he loses less amount each week. Tom's doing best because every kid now understands that this quadratic relationship apparently is going to end up bottoming out at about 188. There's no way at this rate of decline he's going to get beyond that, right? Convince me Jamie's doing best so far. Just consistent dieter, that's great. Kids see constant rate. And then you remind them that says after about 6 weeks of that, you better stop, right? That in fact that is unhealthy to the max. And then the kids all think Ronnie's doing best because she lost the most and all that kind of stuff, right? Yeah, I mean, Ronnie needs to go to the hospital unless, you know, in all those ways, right? Argue that Tom's best, Ronnie's best, Jamie's best, and now express the weight P of each person after W weeks. There you go, gang. We don't start with the damn stupid formulas. We start with the data. We create a graph. We have a table, and then the question is, now can you mathematize it? And that, as you've seen, is what we've talked about all day, is the last piece. And think about how much of our instruction starts with and ends with y equals x squared plus 7x minus 5. Why are we doing this? I don't know. When will I ever do this in the real world? I don't know. But it's on the Ames test, so you better do it. No, gang, there's one stupid item that you saw, and it has nothing to do with the big understandings that we're trying to inculcate in the stuff that we've been doing. Right? And so there's Jamie, there's the weighted matter, and come on. There it is. So, I thought that at this point, I'd have the graphing calculator. I thought that I'd be able to put this on the antique, obsolete overhead projector that doesn't exist anywhere in this building. Because I wanted you to see how, in trying to build quadratics, I reinforce linear and cubic as a look ahead to pre-calculus. I want you to see that what I have here is a 10-meter race. 10 meters. When does Plotter get to 10 meters? 2.4 means that I still have to go 7.6. 7.6 is 3/4 of about 1. Exactly. So 1, 5, 1. That's not going to give me this as a 10. 6. Oh, wait a second. T has to be 10. 10 would then be 7.5. Oh, so after 10 seconds, it looks like Plata would cross the finish line. So far, so good? Does that make sense to you? Wonderful. What happens, where's quaddy after 10? So take out your calculators and do this with me. 0.2 times 10, you all know, is 2. 2 times 10 minus 5.1, you don't need a calculator for this. That's 4.9. 4.9 times 2. Oh, looking pretty close. And then put 10 in this one, and you find that D is also essentially 10. What that means is that I have a linear path of constant change to get from the beginning in. I have a quadratic path that gets me there, and I have a cubic path. When I put them into Y1, Y2, Y3 in my graphing calculator, and I press start, and I have them graph simultaneously, it looks like they all get to 10 at exactly the same time. And so I zoom in and I zoom in and I zoom in, and what's so cool is that you're able to follow this amazing QB path where he speeds up, and one of the most fun things I've ever done with kids is build the functions, there they are, who wins, and then go back and call the race. Call the race, so I guess what you need to know now is that.
Oh.
He's incorrigible. How do you take it off?
Use your finger.
No? Just good. Look at that. Steve comes from, that's right. Emily, you can't pay me for this trip. I owe you $6,000.
Actually, if you go over it with a dryer,
Yeah.
it'll take off there.
Can I use this?
No, because your pen is cut.
So you've got me coming on Thursdays and Fridays starting in November, right? But we're still doing this on Friday, right?
Yes.
It's whatever. I am better on Mondays. No, it's okay. This actually, I think this is great. Because the fact of the matter is, at South Point, there is an amazing amount of use of technology. It's just there, and it's used. Okay? We talked about what's not at Australia, and we saw what is not used in your guys' classroom at Tempe Accelerated. So in fact, I'm sitting here trying to model it, and you see that this got screwed up because I didn't have a tool. Okay? I'm trying to make use of it to show you that even I, as a rookie who doesn't spend my whole life with this stuff, who's not a complete techie freak, because I'm more interested in the problems than I can still take those risks, and then, you know, I've got this in my hand and I want to put it down because God forbid, and now it's out. And so now, notice how artfully I tried to cover it up. Yeah. Where do all three people start?
Zero.
Quaddy starts here, QB starts here. Plotter gets a head start and starts there at 2.4 on a distance of 10. Oh. They all, somewhere around 10 seconds, get 10 meters. So far, so good? Yes? Look what I have here. I have this wonderful sense of when I have my graphing calculator, la 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 la. So far, so good? 0.2 t squared, right? Minus 0.52 goes through 0, 0, out like that. Oh, how interesting. So this is Plotter, this is Quaddy. Does anyone have any idea what QB looks like? You got a graphing calculator? That's right, right? In fact, he sits there and he does this amazing thing like this. Now you go call the race. In fact, he's out there, he wins, he said, and then he goes back, he's going the wrong way, knows what he's doing, he's going backwards on the track, and you sit there and realize that you have or don't have this sense of what these functions mean in large measure on the basis of the way in which that plays out. So all I can do is say, there's one for you to go play with, and all I can hope is that there's one of you in each school who's crazy enough to actually say, I want to see how this really works. And then go share it with one of the others of you. And then go and do it in a class and sort of blow up and have it play and all those things. And finally, gang, where can you start? Where can you end? Because by now you see that I could have started with a skeleton tower and ended with painted cubes. Or I could have started with painted cubes and ended with a skeleton tower. Okay? Because I have these bookends that say, how do I tell you what I'm going to tell you? And then, how do you now tell me that in fact you have learned something that goes on? And so a cube with edges of length 2 centimeters, you got the cube, 2 centimeters, right? Is constructed with centimeter cubes and glued together. Help me with this. A cube, 2 centimeters, is made up of 1 centimeter blocks, cubes. How many are there?
8.
Where did 8 come from?
Mental picture.
Look at that. Some of you see 4 and 4, which is 2 squared times 2. Some of you saw 2 times 2 times 2. How else did you see it? 1, 2, 3, 4, 5, 6, 7, 8? Yeah? Okay, cool. What's the next one up? It's going to be 3 by 3. So you know this famous problem, okay? If the outside faces of the large cube are painted, and then the cube is broken apart, how many of those faces are going to have 3 faces that are painted, 2 painted faces, 1 painted face, and no painted faces? And so, here we go, okay? Nice, clean, sitting there. Excuse me. I watched, and I could have been in any of your schools, 3 or 4 cases today where, for all the right reasons, if you want me to give you the benefit of the doubt, you didn't use technology and therefore wasted 3 and 4 minutes putting something like this on the board, or had kids put it on the board. Look at the difference between having it on PowerPoint, having it on the thing, and being able to go, bingo, let's talk about it. You already told me that, can I write on this now?
You're using the right pen.
Yes, I know. How many of those 8 have 3 faces painted?
4.
12. That's great. There are 8 altogether, and there are 12 that have 3 painted faces. Good. So now we have to go and talk about what the heck I'm talking about. Ah, so there's what I'm talking about, except that it's like this, and like this, and like this, and so there are the 8. I dump the entire thing into blue paint. I pull it out, and I pull it apart. How many cubes have I just pulled apart? 8. How many blue faces on this one right here?
3.
Top, bottom, and side. How about on this one?
3.
How about on this one?
3.
8, 0, 0, 0. So far, so good? Yes?
Yes.
All right. On your mark. Get set. You have 1 minute by yourselves. 1 minute. Fill in that row. And obviously, I'm going to need you to justify it. Check your answers, please.
Yay, I got those answers.
Wonderful. Boys and girls, where'd these 8 come from? I can't hear you. They're the corners. Good. Where'd that 1 come from? That's the one stuck in the middle, right? I got all these on the outside. There's that 1 buried right there underneath this guy here. Good. Where'd the 6 come from? Oh, the 1, it's the 1 in the middle of each face. How cool, right? And where did the 12 come from? There's 4 over here, right? This, right? And then the other side, there's the 4. So they're the ones on the edges. So how interesting. We have 8 corners. We have 6 faces. And we have 12 edges, if you let me just play. All right. 4. Let's see if this makes any sense. 4 times 4 times 4. What is this called? So when I get to n, what goes here? Isn't that nice? My favorite function. What does it look like as a graph? Line. Done, finished, right? Good. Constant, right? There's no variable. It's always 8. Wonderful. All right, so this is 8. Go ahead. Scream it out and tell me why. I want to say it's 24. I want to say it's 18. Where did they come from? Picture it. There are 6 faces. Each of those faces has 1, 2, 3, 4, 5, 6, 7, 8. Those, oh, wait. The 2. Yeah, the 2 here, the 2 here. So that looks like 8. And then the 8 on this side, and then the 8 around. Oh, neat. The 1s. They're the ones sitting in the middle, right? So what are the middles now in each case? You add this up and it becomes a middle that's 2 by 2. 4 times. Am I doing this right?
But you're missing the top and the bottom. Isn't it 6 times?
4 times 6.
Yeah, so the question is, how many and what?
24.
Yeah, it's 24, isn't it?
Yeah.
It's 24 because there are 12 edges, and each of those edges has these 2. Wait a second.
No, there's 4.
No, it's because there are 4 times 6. Of course. Put it down. And in the middle, 8. Oh, nice. This 8 comes from that 8 and all that stuff. Ladies and gentlemen, just like the skeleton tower that gave us a linear pattern for the number in each layer and a quadratic pattern that we saw for the total